So to start understanding logarithms, we're going to start with an exponent, an exponential function. And I also talked about at the beginning of this unit that we study exponents and logs at the same time because they are related to one another. Okay, so we're going to start with this. Sketch the graph of y equals 2 to the x. So let's just quickly, we've done this particular function quite a bit, but let's make a little table of values. And take a look at x and 2 to the x. That would be the y value. Okay? So let's say we do -2, -1, 0, 1, and 2. Okay? So when x is -2, 2 to the -2, what's that equal to? 1 over 4. Okay? 2 to the -1, 1/2. 2 to the 0, 1. 2 to the 1, 2 squared is 4. Okay, so let's plot those points. We've done this a lot already. So we've got -2 1/4, -1/2, 0, 1, 1, 2, 2, 4. We could also do 3, 8. Why not? There we go. Okay, so we end up getting very, very close to the x-axis. This is our horizontal asymptote. And then we're going to sort of increase a lot, actually. Increase exponentially. That's a big increase on the right side. Okay? So what's the domain and range of this particular function? What would the domain be? Yep. And the range? Y is greater than 0 because we have that horizontal asymptote. So no y value will be at the x-axis or below. Okay? X and y intercepts. What's the x-intercept?
I forgot to do graph the inverse using
Oh, yeah, you're right. Okay.
I just have a feeling because the x-intercept.
Yeah. Okay. So you know what? Here's what I want to do, actually. I want to just make sure that we have all of the stuff down for this function. Then I'm going to do the inverse in a different color. Thank you. I was going to come to that, though. Okay, what are the x and the y intercepts of the exponential function? What's the x-intercept of this function? Nothing. The y-intercept is at 1. Okay, what's the equation of the asymptote? It would be the x-axis, which is y equals 0. Okay, now let's think about the equation of the inverse. So when we're looking at a function in its inverse, how do we get from the function to the inverse? Yeah, swap x and y. Exactly. So the inverse would be x equals 2 to the y. So actually, here's where I want to go in a different color. X equals 2 to the y. Graphically, if we wanted to graph the inverse, what would we do? Yeah, swap the coordinates on these points. So instead of graphing -2 1/4, I'm going to graph 1/4 -2. That's about here. Okay? Instead of graphing -1/2, I'm going to graph 1/2 -1. Okay? Instead of graphing 0, 1, I'm going to graph 1, 0. Okay, 1, 2 is going to become 2, 1. 2, 4 will become 4, 2. And I also put in 3, 8 there. That'll become 8, 3. Okay, so this guy is going to look like this. Okay, there's the inverse. All right, so for this inverse, let's go through all of these different characteristics of the inverse function as well. Okay, so what's the domain of the inverse? X greater than 0. We can see that graphically, and that's what it should be, because when you look at a function and its inverse, the domain and range swap. Okay, the range is, in fact, y is an element of the reals, because there's the arrow this way is going down, the arrow this way is going vertically up, right? It's going to the right as well, but it's going up. So the range is y is an element of the real numbers. Okay, what's the x-intercept of the inverse? 1. And the y-intercept? Yeah, there is none. Okay, the asymptote. What's the equation of the asymptote? X equals 0. Now the y-axis is an asymptote, and this is called a vertical asymptote. Okay, so the equation of the asymptote is x equals 0. Here's the equation. Okay, now do we have a way of isolating y that we know of? Yeah? How? How would you isolate y here? Okay, so this is where we're going to bring in logarithms. A logarithm or a logarithmic function is the inverse of an exponential function. And a logarithm essentially is another way, I'm going to skip down here for now first. A logarithm is another way of showing the relationship between a power that has a base and an exponent and its value. Okay, so this is another way to show the relationship. Why can't I spell relation? There we go. Between a power. Power is made up of 2 parts, base and exponent, and its value. So what I mean by its value, if you have 5 squared, the value is 25. Okay? So, for example, let's say I have x equals 2 to the y. In logarithmic form, this is the exponential form. This will become a logarithm with a base of 2. The base sort of goes in the subscript of the value, that's x, is equal to the exponent. Now the value, this is not called the value of the logarithm. This is called the argument. Okay, and essentially a logarithm is a way to isolate the exponent. Okay, it's another way of showing the relationship between the 3 pieces. So a little more concrete. Let's say I have something like 5 squared equals 25. In logarithmic form, I would say a logarithm with a base of 5. Base stays the same. Log base 5 of 25 is equal to 2. And essentially, when you see this, what you are asking is 5 raised to what exponent equals 25? That's what you're asking. Now, why do we have these? Interesting question. Okay, so applications. The most commonly known applications of logarithms are the pH scale, which looks at the level of acidity in a solution, and the Richter scale, which measures the intensity of an earthquake. Okay? In everyday, life outside of math class and physics class and chemistry class, that's where where you might see logarithms the most. Okay? So here's why they're useful. A logarithm is actually equal to the exponent part. So when we use logarithms is when we are comparing, like on a scale, values that have an enormous, enormous, enormous range. And by only keeping track of the exponent, now we're tracking a smaller number, essentially. Okay? So we will get more into the application piece a little later on, but that's really what they're good for. Okay? So let's go back to here. How would you solve for y? We would have to use logarithms. Put this into logarithmic form. Okay, so the isolated piece is the exponent. That would, in this case, would be y equals log with a base of 2 to the of x. Okay, now we're going to talk later on in today's class about how to actually enter that graphically, because you may see a log button on your calculator, but that log button is not log base 2. Okay, so we'll get to that in a moment. Okay? The first thing that I want to do is just practice switching forms. Okay? So when I'm switching forms, I actually just like to write the relationship, especially when you're getting used to these, somewhere above on the page. So let's say I have x equals c to the y, because that base of 2 really could be anything, right? In the previous example, when we were comparing, y equals 2 to the x to its inverse, the base was 2, but it could be any number. Well, there's a caveat to that. In an exponential function, what types of bases can you have? It doesn't have to be whole. Could they be negative? Could you have a negative base? No, and you can't have can't be less than 0, so it must be greater than 0, and it can't be 1. Same thing is going to apply here. Okay? In logarithmic form, we will have y equals log base c of x. Okay? And then when you're rearranging, honestly, you're just plunking things into different places. It's like fill in the blank, right? So if you have blank equals log base blank of blank, what goes where, right? The exponent is the one that's isolated. 3 equals log base 5 of 125. Okay, now this actually makes sense because remember when you're looking at a logarithm and trying to figure out its value, you were asking 5 raised to what exponent equals 125? 5 to the power what is 125? 3. 5 cubed is 125, and that's the value of the logarithm. Okay, here, we would have the isolated part is the exponent, y equals log base 3 of x. Okay, and again, the piece that goes here is called the argument. I actually don't know why it's called the argument. I want to do let me do some research on that because I've never actually questioned why we use that name. But Anyway, that'll be my homework. Okay, here, the isolated part would be the exponent. So negative 2 equals log base 4 of 1 over 16. Okay. And let's go the other way. So log base 10 of 100 equals 2. So what would the base of the power be? 10. What is the exponent on the power? 2. And that's equal to 100. Okay, so actually this reminds me of something that I meant to tell you earlier. I knew I was forgetting something. So just go back to this page. I wanted to add something at the bottom here. Okay, and that is something called the common logarithm. Yes, sorry.
Will there be like questions on the test that make you use the statement argument or understand?
Would you have to refer? You might be asked, what is the argument in this? Yeah, and it's just the piece that goes in the logarithm. Yeah. Okay, so here's what I meant to tell you. The common logarithm is a logarithm with base 10. Okay, when you have a common logarithm, you don't actually have to write the base in. So if you see this, log of x, that equals log base 10 of x. Okay, it's almost like with a radical when you're taking a square root, you don't need to put the little 2 in there. We just assume that we're looking at an index of 2. Okay, same thing with the common logarithm. Now, if you look at your calculators and you find your log button, okay, on this one it's just in there. Actually, I'm going to pull up a calculator. The logarithms, the log button in your calculator is the common logarithm. So that's base 10. Now, all of those logarithms are stored within the memory of your calculator. Okay, so evaluating certain logs with base 10 is not terribly hard. So for example, if I'm thinking about, let's say this one over here, right? And I'm trying to evaluate it. I'm saying 10 to the what is 100? Well, we know 10 squared is 100. So once we practice this, we can kind of get around, we'll be able to evaluate some of these. But what if I asked you log base 10 of 50? So let's go back to the common log. If I asked you log base 10 of 50, essentially what I'm saying is 10 to the what equals 50. Okay, can I do that? Does that work? Well, let's look at powers of 10. 10 to the 0, 1. 10 to the 1, 10. 10 squared, 100. Okay, 50's in here. Somewhere in there. So log base 10 of 50 will probably be between 1 and 2. It will be between 1 and 2. Somewhere in the middle. It's not quite linear though, so it's not going to be right in the middle. But it's somewhere in the middle. Okay, so we could maybe say it's about 1.4 or 1.5. But it is actually going to be an irrational number. And if you enter in log of 50, the log button on your calculator uses base 50. You will see, oh, I was wrong. It was 1.69 whatever, about 1.7. Okay, but it is between 1 and 2. Okay? So these values in your calculator are there because your calculator has a memory and it can hold information. okay? Like, for example, trig ratios. Those are also stored in the memory of your calculator. Logarithms are stored in the memory of your calculator, okay? Now, about 40 years ago, calculators did not have a lot of memory. And so prior to about 40 years ago, people had to carry around these. And this is a figures table. Okay, so your logarithms, your common logarithms, it's all indexed. You've got your logs, your anti-logs, your log sine, cosine, tan, whatever. They're all in here. And you'd have to go up and look at what log 50 equaled. And you'd get a decimal approximation. Okay, so this belonged to my aunt. And it was, I don't know when exactly, it belonged to my aunt and my mom. My mom used it too. And they didn't have calculators in high school. So they had to use these. They worked with trig, they worked with logs, and they carried around these. Okay? And this would have been, my mom graduated from high school in 1965. So this, my aunt in 1963. So this would have been the late 50s, early 60s. Okay? But now you're lucky all of that is stored in the memory of your calculator for base 10. Okay? There is one other base that's also stored in the memory of your calculator, which we're not going to get into too much this year, but if you take calculus, you will. And that's called the natural logarithm. And that is a logarithm with base e. E is an irrational number that's sort of like pi. Okay? And it's about 2.7. That's really all you need to know about it. But what we use for natural logarithm is ln. And ln is equal to log base e. So ln x is log base e of x. Okay, and e is approximately 2.7. Okay, so back on your calculator, if you don't actually have an e button, but you have an e to the x button, that's right here. So I'm just going to put in e to the 1 because that's equal to e. And there you go. It's about 2.72. Okay, so the logarithms with base e are also stored in the memory of your calculator. That would be the ln button. So if I actually put in ln of e, I'm saying, whoops. E raised to what exponent equals e? That would be 1. E to the 1 equals e. So this will equal 1. Okay? But again, you don't really need to know too much about it this year. But I do want to just tell you that it exists, and there are lots of applications that involve both an exponential function with base e and the natural logarithm if you take calculus. It has some pretty cool properties, actually. Okay. So back to here. We're going in the reverse order. So we're, again, just practicing switching forms. I just remembered when we did one with base 10 that I forgot to mention that. Okay, so here we're going into exponential form. The base is the same as the base of the log. So this would be 6. The exponent is what the log is equal to the negative 2. And that's equal to 1 over 36. And that's true. That's 1 over 6 squared. 1 over 6 squared is 1 over 36. Okay, and here we will have the base will be 2 to the exponent 5 over 2 is equal to the square root of 32. Okay, now this is also true because this guy in radical form is the square root of 2 to the 5. 2 to the 5 is 32. Okay? All right, so evaluating these things. I've already sort of hinted at this, and there are a couple of ways that you can do these. When you practice them, you'll probably be able to do them fairly quickly in your head. But what I want to do is show you a way of evaluating them so that we can get an understanding for how to do this sort of quickly. Okay, so when I'm evaluating a logarithm, just to start, what I'm going to do is I'm going to set this equal to a variable. I'm going to set it equal to a variable, and I'm going to switch forms. I'm going to switch to exponential form. So in exponential form, the base will be 3. The exponent is x, and the value is the argument. It's equal to 27. Okay? So what I have essentially done is created an exponential equation, which we looked at yesterday. Okay? Now, to solve an exponential equation graphically, we can use change of base. So if I can write 27 using a base of 3, which I can, it's equal to 3 cubed, then I can drop the bases and conclude that x equals 3. Okay? Now, do you have to do this every single time? No, not at all. What I actually want you to see is that you can actually switch this into logarithmic form within the logarithm. So if I take log base 3 of 27 and write that as log base 3 of 3 cubed, that will equal 3. It's equal to the exponent. Because essentially what this asks is 3 to the what equals 3 cubed. It's got to be 3 to the 3 equals 3 cubed. So if you can write the argument using the base of the logarithm, the value of the log will simply be whatever the exponent is. Okay? So let's just try one more. And we'll do it sort of the longer way first, and then we'll cut to the chase. Okay, so here we've got log base 7 of 1 over 49. I'm going to set that equal to a variable. And I will now, in exponential form, have 7 to the x equals 1 over 49. Okay, and the goal here, if I'm solving an exponential equation, is to get a common base. So I can write 49 as 7 squared. So this becomes 7 to the x equals 1 over 7 squared. And then I have to bring it up, right? So x equals -2. Okay, no problem evaluating these this way at all. You can do this every single time if you want. But what I suspect will happen, because this is usually what happens, is that you will start to think that, okay, log base 7 of 1 over 49. I can write 1 over 49 as 7 to the -2. So I'm just going to think that's log base 7 of 7 to the -2. 1 over 49 is 7 to the -2. This basically asks 7 raised to what exponent is 7 to the -2? 7 to the what equals 7 to the -2? It's got to be -2. Yeah, so as soon as you get it into this format, there you go. And in general, this is true, okay? Log base a of a to the n equals n. This is not going to be on a formula sheet, but it is pretty handy to keep in mind. Okay, so let's go back to this guy. This is log base 2. I know I'm scrolling too much, but this question over here that's not on the page, log base 2 of 2 to the 7.
It's equal to 7.
It's 7, yes. Okay, so this guy's equal to 7. All right. So far, so good? Okay. So now what we're going to do is practice evaluating these things. Okay? And the fastest way to do this, and what I'm going to encourage you to do, is to try, if you can, to express the argument as a power of the base. how can I write, firstly, what base is this? 10. Now, when it's in decimal form, sometimes I like to think, okay, what would that be as a fraction? This is 0.01. That's 1/100ths. Okay, so the question is this. How can I write 1 over 100 using base 10? 10 to the negative 2. Yeah, because it's 1 over 10 squared. So this will be negative 2. Yes?
So is logarithms, is it just involve like the logs from mental math?
It does involve, yeah. So when you're evaluating logs, there is a lot of mental math involved. Okay? Now, what we're going to get into a little later is what happens if you actually can't evaluate it. Like, what if you get log 50? Then what? Okay, and then we'll talk about that as well, because they do also involve a lot of irrational numbers. Okay, so we're going to do some work on that as well. Yeah?
When writing it, like if that's a base of 10, do you have to write log 10 or you can just write log?
No, you can just write log. Yeah, absolutely. If you don't, and in fact, if it was a different base and you didn't include the base, it would be wrong. But with base 10, you don't have to put it in. Yeah. Okay? All right, this guy. So this one's kind of tricky. But our base is 9. We're taking a fifth root of 81. So is there anything there that I can replace with base 9? Ignore the root for now. The 81 is 9 squared. So I'm going to start with that. Log base 9 of the fifth root of 9 squared. Okay, now this is not an exponential form yet. This is a radical. How do I go from radical to exponential? This is going to be a fractional exponent, right? What goes in the denominator? Yeah. Yeah, so the index becomes the denominator. So that's log base 9 of 9 to the 2/5. So this will equal 2/5. Okay? Okay, so now we are solving an equation. So when solving an equation, you almost always have to switch forms. And in fact, when people are solving exponential equations or logarithmic equations and they're stuck, the first go-to is switch forms. If you're in exponential form, switch to logarithms. If you're in logarithmic form, switch to exponential form. Okay, so that's what we're going to do here. The base of our exponent, or power rather, would be 16. The exponent is negative 1 over 4. Okay. Now, evaluating 16 to the negative 1/4, there are multiple ways that you can do this. If you want to do it the way you learned like in Math 10C, you would have to deal with both the fact that you have a negative exponent and the fact that you have a fractional exponent. And you can do that one at a time. So for example, I could convert it to a radical first. So this would be the fourth root of 16 to the negative 1. What's the fourth root of 16? What times itself 4 times is 16? 2. So this is 2 to the negative 1 equals x, and that's a half. Okay? But now that you know change of base, you could also, this doesn't work every time, but if you have 16 to the negative 1/4 equals x, change the base there. That's 2 to the 4. Okay? These get multiplied together, and the 4's cancel. So this exponent, 4 times negative 1/4 is negative 1. So that's still half. Doesn't change. Okay? Okay, this one is kind of neat. So in this case, we don't know the base. We don't know the base. So that's going to be our variable, our unknown. Okay, so in exponential form, the base is x. The exponent is 2/3. That's equal to 9. Okay, now I want to isolate x. If I isolate x, I have x to the 1. This is now x to the 2/3. What exponent could I raise this by to make, when I multiply them together, the product equal 1? 3/2. So that's what I'm going to do on both sides. Okay, now this side becomes x to the 1, because it's 6/6 is 1. Okay, now this side, there's two ways to do it, radical form or switch the base here. So in radical form, this would be the square root of 9 cubed, which is 3 cubed, which is 27. Okay, or you could also go put this as 3 squared. So 3 squared, 2 times 3/2 is 3 to the 3, and that's also 27. Okay, and finally, log base 4 of x equals -2. So we're going to switch forms again. And our base will be 4. Our exponent is -2 equals x. Okay, x is already isolated. This is nice, so we just have to evaluate that. That's 1/4 squared, and that's 1/16. So when in doubt, switch forms. Okay. So evaluating these things with a calculator. You only have 2 bases on your calculator. Okay. You have base 10 and base e. Okay. So let's say, for example, I had something like this. Log base 2 of 11. Can I do that algebraically? I'm asking 2 to the what equals 11. Is there a number that I can figure out? Can I write 11 using base 2? No. So this is going to be irrational. Okay? So the only way to evaluate it, and in fact, we're only going to approximate it if we put it into our calculator, is by doing something called changing the base. Now, honestly, I don't actually like to introduce this before I do log laws, because what I'm going to do next week is prove this to you. But change of base, and this is actually on your formula sheet, works like this. If you have a logarithm with a base a, log base a of b, you can change that logarithm into whatever base you want. Introduce a new base. And it's equivalent in this way. Log base a of b is equal to log base c of b over log base c of a. Okay. Now, 99.9% of the time, what do you think we would choose to be c? 10, yeah, because that's what's in our calculator. And so now we can use our calculator to do this. So the base could be whatever you want. It could be base pi if you want, right? That would be fine too. But almost always we use base 10 because that's what's stored in the memory of our calculator. Back in the 50s and 60s, that would be the base that's stored in your logbook. So you can get the decimal, put the 2 decimals in. You know, the math would not be very fun because you're dividing a decimal by a decimal, but it could be done. Okay? So this is going to equal to, I'm going to use base 10. log base 10, I always set it up like this. And again, because you're choosing 10, that does not need to go in there. But I just want to sort of emphasize the fact that this is our new base. Argument over original base. Okay, and again, this is on your formula sheet. Okay, now I hate dropping things out of the sky and saying use it. I hate that. Because there's always in mathematics a proof or a reason as to why we do things. So what I'm going to ask you to do is to stay tuned because we need to know our log laws. And the log laws also, foreshadowing, are sort of the analogous exponent laws in logarithmic form. Okay? We got to know those to prove the change of base law, but I will do that for you next week. Okay? Now, why is this useful? Number one, we can now approximate these logarithms. So I can put in here log 11 divided by log 2. And there's my approximation. It's about 3.46. Okay? But the other reason why it's useful is that if you have a function that does not use base 10, you have to be able to enter that function into your calculator. So the function that we looked at, I'm just actually going to continue this down here because you guys know I write big. Okay, the one that we looked at was y equals log base 2 of x. Okay. Without the change of base law, we can't put that into our calculator. So we would have to change this into log over log, right? The base of 10, I'm not actually going to put that in. That goes in the numerator. The original goes in the denominator. Okay, so on your calculator, if you wanted to graph that function, oh, actually, there's something else that you guys need to know about these. I'm glad that I'm thinking about this. We would have to go log x divided by log 2. Okay, and I'm going to go zoom standard. Okay, now, this is another thing that you guys need to know. This is where, like, calculators have limitations. Looks to me like that graph starts there, like there's an end point. But what did we actually know happens here? There's a vertical asymptote, yes. So here's the limitation of your calculator. And actually, to be honest, I don't know if this is the case on the Casio. I'm going to look in a minute. You might actually see that vertical asymptote on the Casio. TI calculators will only graph functions. And when you look at this, the calculator, because it's so close to the y-axis, cannot actually distinguish the difference between this function over here and a vertical line. And so it's going to cut it off. Now, you need to know that that doesn't actually happen. And you can actually, if we zoom in a little bit, it looks like this starts at about y equals -3, right? So it looks like the minimum value is at about -3. If I change the window setting to just zoom in over here, I'm going to make the x min 0 and the x max 100th. 0.01. So I'm really just zooming in on that tiny, tiny, tiny little domain. You'll see, because it's stretching it out, it goes way lower than that, right? Here, it's below -10. So when you zoom in, it doesn't look like a vertical line. Okay, so you need to know that it is not an endpoint. It is, in fact, a vertical line. Okay? Okay, so that's basically right now why you need to know change of base, because you may have to enter these functions into your calculator. Okay? Now, I know someone in the class is going to be like, my calculator has a log button where you can enter in whatever base you want. And that is true. A lot of the newer models do. Okay, so I can't remember exactly where it is, to be honest. because this calculator is very, very old, and it doesn't have that. I think I have it on my, I think it's under the math button, but I can't remember, okay? If you have that, great. But what you do need to know is that your calculator doesn't store those bases. Your calculator has an algorithm in it that applies the change of base law. Okay? Not all calculators have this button. If you think yours does, I can help you find it later. Okay? At the same time, though, you may be asked a question, I've seen this on diploma exams before, that specifically asks about change of base law, so you do need to know it. But there are workarounds to doing this depending on your calculator. Okay. Last question of the day. The largest measured earthquake struck Chile in 1960, measuring 9.5 on the Richter scale. How many times as great was the seismic shaking of the Chilean earthquake than the 1949 Haida Gwaii earthquake, which measured 8.1 on the Richter scale? Okay. Now, here's what you guys need to know, and this may not be given to you in the question. The Richter scale is equal to log base 10 of the intensity. Okay. Ooh. You okay? Whew, I thought maybe an earthquake had happened or something. You sure? You're good? Okay. Don't have to do any first aid? All right. So, what that means is that when you have an earthquake that measures, let's say, 5 on the Richter scale, that 5 is actually the exponent on 10. So the intensity is 10 to the 5. If you go up 1 point to a Richter scale reading of 6, your intensity is now 10 to the 6. So you have actually increased tenfold in intensity. If you're 2 away, the intensity goes up by 10 squared. Okay? So it is a logarithmic scale. And the reason, again, why we use logarithms is because the intensity scale is so large, right? You can have a tiny, tiny intensity or an incredibly large intensity that just keeping track of those numbers that are in the thousands, hundred thousands, millions would be a lot to keep track of. And you could lose a 0 or whatever, right? So we do this exponentially. Okay? So what that means is that if we look at Chile, the 9.5 is equal to log base 10 of the intensity. Now, if we actually wanted to evaluate the intensity, we'd have to switch forms. The intensity, right, becomes the value of the power, is 10 to the 9.5. Okay. In Haida Gwaii, that's 8.1. is equal to log base 10 of the intensity. Okay, I'm actually going to label this as intensity C, and this is HD. If we switch forms here, the intensity for Haida Gwaii is 10 to the 8.1. Okay, so if we wanted to compare, how many more times intense is this one than this one? We have to take their ratios. Okay, so 10 to the 9.5 over 10 to the 8.1. You could do that all on your calculator, or you could use your exponent laws. This is 10 to the 1.4, subtract. Okay, and essentially what this is, it's the intensity ratio. So this is the intensity of Chile over the intensity of Haida Gwaii. Okay. That is, I don't know. It's going to be like 20 something. What is it?
Yeah,
25 times more intense. Okay? It's a lot of damage that can happen in 25 times more intense. Okay, so I'm going to end there for today.